I'm going to show you why this series in particular gets a lot of hate.
Oh, there is a very good reason why that equality gets hate, and it's because it makes no sense.
We can make some sense out of this value, negative 1 over 12.
We can absolutely make sense of that number minus 1 over 12. It's called construct the analytic continuation of the Riemann zeta function and evaluate at minus 1. Please do that.
I'm going to take this divergent series and I'm going to replace it with a better, let's say, convergent series.
Please replace it with the analytic continuation of the Riemann zeta function, please.
So what I'll do is I'll take the sum, I'll take the n, and then I will smooth it out by introducing this exponential.
Of course not. Why will the physicists just do anything but what we know that works from a rigorous mathematical point of view, which is extend analytically?
Somehow, interestingly, weirdly, surprisingly maybe, we also got a constant term. And this constant term just magically appeared to us. It's negative 1 over 12.
Yes, of course, there is something to that minus 1 over 12. It's the value of the analytic continuation of the Riemann zeta function at minus 1. And that's the one and only way to explain that number in relation to the sum of the natural numbers. Moreover, there are so many steps here that are just not done rigorously. For one thing, when t goes to 0, these will go to infinity, and it doesn't matter there is a constant there, the whole thing will blow to infinity. Second, there are several places where limits are exchanged without justification. The derivative of an infinite sum is the infinite sum of the derivatives, or the limit of an infinite sum is the infinite sum of the limits. All those steps need justification to justify these values that showed up.
That's what it's all about. This is why people assign this a value of minus 1 over 12, especially in string theory, to get meaningful results.
In the fact that the string theorists can replace the sum of the natural numbers by minus 1 over 12 and make some sense out of it, that just means that they are making 2 or 3 mistakes, mathematical mistakes in a row that they're canceling out and somehow getting a result that makes sense at the end of the day. What I think is happening is that if string theorists learn how to use analytic continuations, they might actually come up with a rigorous way to explain this value of minus 1 over 12 in their calculations. It's just about time that physicists start using the work of Riemann in the 1800s on the Riemann zeta function. The analytic continuation of the Riemann zeta function was proved by Riemann in 1859 in his paper on the number of prime numbers less than a given quantity. So let's see how to compute the value of the continuation of the analytic continuation at s equals minus 1. This is the formula of the usual Riemann zeta function, but the Riemann zeta function as is only converges for complex numbers whose real part are bigger than 1. And what Riemann proved is that we can find another complex function, which I'm going to call z of s, that extends the Riemann zeta function to the entire complex plane. Now, the function z of s and zeta of s coincide to the right of 1, but it has a completely different definition to the left of 1. To compute values of the analytic continuation of z of s to the left of 1, we use what we call the functional equation, which is the following that relates values of s with values of 1 minus s. So values to the right of 1 with values to the left of 1. So to compute the value of z of minus 1, I can just plug in my functional equation at minus 1 and evaluate all these quantities. For example, sine of minus pi over 2, that's minus 1, gamma of 2, that's just 1, and z of 2, that's the Riemann zeta function, the usual Riemann zeta function evaluated at 2, which we know is the sum of 1 over n squared, and that is well known to be pi squared divided by 6. So I can plug in all those values, and what I get is that the value of the analytic continuation at minus 1 is a half times 1 over pi squared times minus 1 times pi squared divided by 6. And when you simplify, you get minus 1 over 12.